Hello friends, welcome to week number 10 where we are going to talk about probably the most common parameter that you can think about in any engineering application, that is the temperature, and we are going to discuss about different methods of measuring the temperature. In fact, why only engineering? If we just forget engineering or forget science, if you just think about our normal day to day life, or just think about the normal life of any common individual who does not have any relation with any kind of technical field, still he knows about the concept of temperature, or at least he definitely makes use of the concept of temperature in some of his daily activities. Like you definitely can remember that when you are a kid, the your parents, maybe your father or mother, with a very worried look, is putting up a small glass stick below your armpit or below the tongue, just to check your body temperature, just to ensure whether you have fever or not. Or say the people who cook in our houses, the entire idea of cooking is just to heat the food stuff to a particular temperature and maintain that temperature over a particular period of time to ensure that your food is properly cooked. Think like about a pressure cooker there. The entire idea of pressure cooker is to increase the pressure inside the container so that we can maintain a higher saturation temperature inside that. As the pressure increases, saturation temperature of water also increases. Like under common atmospheric condition, the saturation temperature of water is about 100 degrees Celsius, whereas when you can make the pressure double, the temperature, saturation temperature is approximately 120 degrees Celsius. So, the entire idea of pressure cooker is to increase the pressure inside so that we can maintain a higher temperature, and therefore, we can boil the foods in a better way. So, this way we can always make use of temperature or the concept of temperature in every day to day activities of ours, and that is why this is probably the most sought after parameter, most discussed or most employed parameter in any kind of human activities. Or okay, I should say this is probably the second most sought after parameter, because time has to be the most sought after parameter that we have to make use of. Everyone needs to know about the concept of time for anything he or she wants to do, but then comes the temperature, and that is why probably intentionally we have kept this module towards the latter part of this course, when we have already finished discussion about topics like pressure or flow or displacement, etc. Mostly because you may already be knowing a few of the ways of measuring temperature, but I am sure I can introduce also several other ways of temperature measurement which will definitely be new and you will definitely find that interesting. Now, before we start, I would like to go for some initial discussion like we have been doing in all the previous modules. Like in the topic of flow measurement, we started with some basic concepts of fluid mechanics, develop the Bernoulli's equation, because that is something that we made use of in the subsequent discussions. In case of force measurement, we started with the discussion on the Newton's second law of motion or Newton's laws of motion. Similarly, we have to define the topic pressure before we started pressure measurement. So, we shall be following the same approach here instead of directly jumping to any kind of instrument. And that is why the first question that I would like to ask you is, what is temperature? You definitely know what the temperature is, but can you define it? Because the most common way we define temperature is something like this feels hotter than the other one, and that is why it definitely is at a temperature higher than the other one. Like suppose if I provide you two sticks, one this one, another this one, and if I ask you which one is at a higher temperature, probably you will try to just sense which one is feeling warmer than the other. If this one is feeling warmer, then you may be saying that this is at a higher temperature than the other, but that is a purely relative way of defining temperature and not a quantitative one at all, because it may well happen that both may be at the same temperature, but one just feels warmer or cooler than the other. Like very common example, like in a cold winter night, if you keep one metal stick and one wooden stick outside throughout the night, and then in the morning if you touch them, then the metal one definitely feels much cooler compared to other one, despite both being at the same temperature. Both are exposed to the same environment for same duration of time, and therefore they must be at the same temperature. However, the metal has an ability to transfer heat to your body much quicker, or I should say in this case absorb heat from your body much quicker compared to the wooden one, and that is why that feels much cooler compared to the other despite they being at the same temperature. Therefore, this relative way of defining temperature is not the perfect one. We must find a proper technical definition of temperature, or at least some kind of scientific base based upon which we can define temperature, and that is not possible from any other laws of physics. Rather, we can define it only when we make use of the concept of the zeroth law of thermodynamics. I am sure you know about the zeroth law, but still I am repeating this one here to clarify the concept of temperature. So, from the concept of zeroth law we know that suppose I am taking three systems here like shown, system A, B and C. So, if two systems say A and C are in thermal equilibrium with each other, and similarly B and C are also separately in thermal equilibrium with each other, then A and B also has to be in thermal equilibrium with each other. Now, what do we mean by thermal equilibrium? Thermal equilibrium means there is no heat transfer that is taking place between the two systems. Or if I take just a single system like this, so this is your system and outside the system you have the surrounding, because you know from thermodynamic point of view anything outside the boundary of a system is surrounding. And now if the system and surrounding are at the different temperature, let us say the system temperature is T sys, the surrounding temperature is T sir. Now if the system temperature and the surrounding temperature they are not equal, then there will be some kind of energy exchange between them, and that energy exchange we call the heat transfer, because heat is defined as the form of energy which can cross the boundary of a system only because of a temperature difference between system and surrounding. Now when those two temperatures are equal, or I should say the system is in thermal equilibrium with the surrounding, then there will be no heat transfer at all. So the concept of thermal equilibrium is related to whether there is any heat transfer taking place or not. There can be some other kind of energy interaction between system and surrounding, or even in terms of this example there may be let us say the system C is the surrounding and system A is the system. Then if there can be some other kind of energy interaction like work interaction or mass interaction, but if they are at thermal equilibrium, then there will be no heat interaction between them. Similarly, when B and C are in thermal equilibrium, then there will be no heat interaction between them. Now, zeroth law says that if A and C are in thermal equilibrium and B and C are also in thermal equilibrium, then A and C must be also in thermal equilibrium. That is, instead of taking A and B separately in contact with C, if we take A and B in contact with each other, then there will be no heat transfer between them because they are at perfect thermal equilibrium. And when that is possible, I have already mentioned that is possible only when this system and surrounding, or in this case system A and B are at the same temperature. So then how we can define temperature? Temperature is a property which defines whether these two systems are in thermal equilibrium or not. Or in a way you can say that when system A and B are in thermal equilibrium, then the property which is equal between A and B is temperature. So if the temperature of system A is Ta and that of C is Tc, then they will be in thermal equilibrium only when Ta is equal to Tc, so that there is no heat transfer. Similarly, if the temperature of B is Tb, then B and C can be in thermal equilibrium only when Tb is equal to Tc. Now, when yes both Ta and Tb are equal to Tc, so Ta and Tb must be equal to each other, that is temperature. So temperature is the property which must be equal between two systems, or maybe between a system and its surrounding, in order to have a thermal equilibrium between them, so that there is no heat transfer at all. So this is the zeroth law of thermodynamics which defines the concept of temperature. Now instead of considering three different systems A, B and C, if we replace this C with a device which is separately in thermal equilibrium both with A and B, then that provides us a way of measuring the temperature, and that is the entire idea of thermometry, which is where we have object A or system A and system B, and the C is a thermometer which is actually a temperature measuring device. Now here I would like to clarify one term. The term thermometer does not refer to only that glass tube that you kept on using from, or you kept on seeing from your childhood. Thermometer refers to any device which can measure temperature. So that glass tube that is that mercury filled capillary tube, that is only one of the examples of a thermometer which have a specific name, and we shall be talking about that later on today. But thermometer, the term thermometer refers to any temperature measuring instrument. Now, let us replace the system C with a thermometer. Then if A and C are in thermal equilibrium and separately B and C are also in thermal equilibrium, then A and B must be at the same temperature. Now, if we know the temperature of this object A, Ta, but we do not know the temperature of Tb, then what we are going to do? If we take the thermometer C in contact with temperature A, and the reading that we are getting, that we are defining as this Ta. Now, if we take this in contact with this object B or system B, and if we get the same reading, then the temperature of this one must be equal to Ta. So, that is the idea where this A acts as the standard, or you can say acts as the reference, where B is the subject of measurement and thermometer is the measuring tool. So, the entire idea of the thermometry starts with this 0th law of thermodynamics. Now, what is the unit of temperature? There are several scales of temperature, but the SI unit of temperature you know is Kelvin. Kelvin is defined as, actually this graphics has a little bit of error, this should not be small k, it has to be capital K, because that unit of temperature is called Kelvin, or SI unit of temperature is called Kelvin to honor the great scientist Lord Kelvin, and that is why this K has to be capital 1. Now, the unit for temperature is Kelvin, which is defined as the distance between the absolute 0 and the triple point of water by 273.16 number of equal parts, then the division or each subdivision is called 1 Kelvin. That is, triple point of water, which is an universal constant, is given a value of 273.16 Kelvin, and absolute 0 is given a value of 0 Kelvin, and correspondingly whatever we are getting, that is 273.16 Kelvin. We shall, but this is not the only scale, there are several other scales also, like the very common one, Celsius and Fahrenheit scales. The term Celsius scale is based upon the name of its inventor, the French technician, or this Celsius, whereas the Fahrenheit scale is in the name of the German inventor Gabriel Fahrenheit, who were the persons to propose this more or less at the same time or around the same decade in early 19th century. Now, both these two temperature scales have something in common. In both cases, we need to specify two standard reference point. That is why they are often called 2-point temperature scale. We need to specify the reference value or some value at 2 points, and the common choice for these 2 points are, one is called the ice point. Ice point refers to the point at which, or the temperature at which under atmospheric condition water starts to condense, or in the reverse way we can say the steam starts to melt. So, in Celsius scale, ice point or the melting point of water is given a value of 0, whereas in Fahrenheit scale that is given a value of 32. Similarly, the second point is called the steam point. Steam point refers to the temperature at which normal water, or I should say water under atmospheric condition starts to boil, or the liquid to vapor phase conversion for water under atmospheric condition starts. That temperature is called steam point. Now, in Celsius scale we call the steam point as 100, and in Fahrenheit scale we call that 212. So, in Celsius scale the distance between the ice point and steam point is 100 units, whereas in Fahrenheit scale the distance is 180 units. So, what we do in either scale, we specify the ice point and the steam point with the corresponding values, and then the distance between these two, that is 100 unit in case of Celsius scale and 180 units in case of Fahrenheit scale, they are given equal divisions. We hardly go for calibration at some intermediate temperatures, like we hardly take any reading at 20 degree Celsius, 40 degree Celsius, or maybe 100 degree Fahrenheit. We rather just make equal divisions, which may always not be true depending upon what kind of scale you are using. Now, one thing you have to remember here, the choice of these values are completely based upon us. That is, the value of 100 specified to the normal boiling point of water or saturation temperature of water under 100 degree Celsius, that under atmospheric condition, that is our choice. We could have easily called that 1000, there is nothing to stop us, or you can easily define a new temperature scale and give it your name. Where you are going to specify the, you may specify the ice point to be given a value of 100 and the steam point to be given a value of 0, and you are coming in the opposite direction, means as the temperature increases the value will decrease in this. There is no harm in that. This will again be a perfectly correct thermodynamic temperature scale as long as you can make equal division between the two. But this all these are 2-point temperature scale. There is also something called the single point temperature scale, but I shall be coming back to that later on. But the idea of 2-point temperature scale, I repeat, is to specify 2 reference point, and the common choice for reference points are the ice point and steam point, and in every temperature 2-point temperature scale these two are given some values, and all the intermediate values or all the intermediate range is divided into equal subdivisions. The Celsius scale earlier used to be called the centigrade scale because we are using the value 100, some resembles to that, but from 1948 onwards the term centigrade has been dropped and we use only the term Celsius. Fahrenheit scale, probably you have, what is the one you are introduced for the first time, because the medical thermometers which we use commonly for measuring the body temperature are generally given in Fahrenheit scale, where the standard human body temperature is around 98.4 degree Fahrenheit, whereas the ranges commonly are specified something like 92 to 110 degree Fahrenheit or maybe 95 to 110 degree Fahrenheit. Generally below 94-95 degree Fahrenheit and above 106 degree Fahrenheit, it may become fatal for human body. In Celsius scale, as it is shown, it is degree Celsius is the unit, but in case of Fahrenheit scale it is degree Fahrenheit. Now, how we can develop a relation between them, something a very school level stuff, as we are taking equal division between them, so you can go for a linear interpolation. So, in case of Celsius scale, if any temperature is given as C, then C minus the ice point temperature, that is 0, divided by steam point temperature 100 minus ice point temperature, that will be equal to F, the corresponding temperature in Fahrenheit scale, minus corresponding steam point value, or sorry, ice point value, which is 32, divided by steam point value 212 minus ice point value, or in the denominator you can also visualize this one to be the number of divisions. So, it becomes C by 100, because there are 100 divisions between the ice point and steam point in Celsius scale, is equal to F minus 32 by 180, as there are 180 divisions in case of Fahrenheit scale, or if we simplify it becomes C by 5 is equal to F minus 32 by 9, a very well known relation which you must have used earlier, or any value in Fahrenheit scale. Therefore, Celsius being much more common nowadays, so if we want to measure any Fahrenheit value, then F will be equal to 1.8 times C plus 32, or if we are interested in the C value, then C will be equal to 5 by 9 into F minus 32. So, this way we can convert between either scales. But Celsius and Fahrenheit scales are not the only one. There are also absolute temperature scales which can be visualized as extension of these scales only. However, practically speaking, they are different temperature scales. If we extend this one to include 2 more scales, where we have the Kelvin, which can be visualized as an absolute temperature scale, absolute temperature extension of Celsius, whereas we can have Rankine, which is the absolute extension of the Fahrenheit. So, in case of Celsius scale, as I have mentioned, the ice point is 0 and that is 32 in case of Fahrenheit scale, that is given as a value of 273, or to be more precise 273.15 in case of Kelvin, and 492, or to be more precise it is 491.67 in case of Rankine scale, and then correspond the remaining extension we can do in both higher side and lower side. So, if we want to derive a relation between Kelvin and Celsius scale, any reading in Celsius scale will be the corresponding value in Kelvin scale minus 273.15, or the value in Kelvin scale will be equal to C plus 273.15. Similarly, any value in Fahrenheit scale will be equal to R corresponding in value in Rankine scale minus 459.67, or the value in Rankine scale will be value in Fahrenheit scale plus 459.67. Actually, Kelvin and Rankine scales are called single point temperature scale. Why they are called that we shall be discussing shortly. But whenever we are talking about in single point temperature scale, generally the degree symbol is dropped. Like 2 point temperature scales, we use the units as degree Celsius and degree Fahrenheit. However, in case of single point temperature scales or absolute temperature scale, we use only K to designate Kelvin and only R to designate Rankine. So, these are the most common temperature scales that we can think of. However, as I have mentioned, you can easily define any 2 point temperature scale by choosing your own values of ice point and steam point, or own values at ice point and steam point, and then taking equal number of divisions in between two. Then subsequently you can extend in either direction, that is below the ice point or above the steam point, just following the same pattern of the subdivisions. Now, we started with the 0th law of thermodynamics. Let us extend a bit more in terms of thermodynamics, and let us talk about the first law of thermodynamics. Now, first law of thermodynamics tells that the change in internal energy of any system during a particular process depends on the net interaction between system and surrounding. If Q is the amount of net heat interaction and W is the amount of net work interaction is taking place, then corresponding change in internal energy will be the summation of these two with the direction being taken into account. Or in differential way we generally write dE, that is change in energy of the system during an infinitesimally small process, will be equal to del Q minus del W, where del Q is the amount of heat transfer to the system during this infinitesimally small process, and del W is the amount of work done by the system, that is work transfer from system to our surrounding during the same process. And this is during a particular process. If we want to analyze a system, then we have to do this for an entire system and sum all of them up. Like, think about a particular cycle, let us plot that on any property diagram. Let us say we take a PV diagram. So, we pick up any standard process. Let us say our process initially starts with a compression process starting from point 1 and going to point 2, which is at a much higher pressure and low volume. Then we have a constant pressure, that is isobaric expansion process, during which pressure remains constant but volume increases to 3, and then we have another process during which the system comes back from 3 to 1. So, now if we want to apply the first law of thermodynamics on this particular process, then integrating this particular relation over each of the processes, we can write during process 1 to 2, we can write E2 minus E1 is equal to Q12 minus W12, where Q12 refers the amount of heat interaction, that is the amount of heat transfer to the system during this process 1 to 2, and W12 refers the amount of work done by the system during this process. If the direction of heat transfer and work transfer are opposite to the one that we are considering, then you have to put a minus sign. During process 2 to 3, you have E3 minus E2 is equal to Q23 minus W23, and then during 3 to 1, you have E1 minus E3 is equal to Q31 minus W31. Now, if we add all of them up, then you have 0 on this side, is equal to summation of all these Q's minus summation of W's, or in a way generally conventionally write them as cyclic integral of del Q is equal to cyclic integral of del W, that is net heat transfer to the system over a cycle is equal to net work done by the system over the same cycle, as E, that is energy, is a property. Here mind you, this E or energy actually is talks about the total energy content of the system, which generally has 3 counterparts, 2 macroscopic part and 1 microscopic part. Macroscopic part in the form of change in kinetic energy plus change in potential energy. These are the two ways system energy can change from macroscopic point of view, plus we have the internal energy, which is a summation of all possible microscopic forms of energy. Practical cases, these two may be extremely small compared to this one. In that case, you can replace this dE with du, but mind you, this is possible only when the changes in kinetic and potential energies are negligibly small compared to the change in internal energy, or to be more specific, you are talking about a stationary system. Stationary means there is no change in kinetic or potential energies. Now, this first law of thermodynamics never talks anything about the temperature. It just talks about the heat and work interaction, but that gives us one useful relation that we are going to make use of very shortly. That is the concept of a heat engine. A heat engine talks about a system working over a cycle. During one part of the cycle, it is drawing QH amount of heat from a high temperature reservoir TH. During another part, it is rejecting QC amount of heat to a low temperature reservoir kept at TC. Here TH is greater than TC, and during another part it is producing this work output W. Such a configuration is called a heat engine, when it is taking heat from a high temperature reservoir, converting a part of that to work output and rejecting the rest to a low temperature reservoir. Now, if we apply the form of the first law of thermodynamics on this cycle, then you have just seen that cyclic integral of del Q is equal to cyclic integral of del W. Now, there are two heat interactions shown here. So, accordingly we can write QH minus QC, because QH is added to the system, that is positive, QC is going away from the system, so that is negative as per our sign convention, is equal to del W. There is only one work interaction shown, which is being done by the system, so it is positive, so that is equal to W. Now, if we want to define an efficiency of this heat engine, efficiency is defined as work output divided by amount of heat added to get this work done. So, using the previous relation from first law, it is QH minus QC upon QH, that is 1 minus QC upon QH. So, the efficiency of a heat engine can be derived just from the knowledge of these two temperatures without bothering about the just from the knowledge of these two heat interaction QH and QC without bothering about the values of this temperature TH and TC. This one we can make use of in conjunction with the second law of thermodynamics. Now, second law of thermodynamics, there are several statements possible from this, but generally there are two very popular statements, and out of which we are going to take the one that is generally called the more fundamental, which is the Clausius statement. According to the Clausius statement, it is impossible to transfer heat from a high temperature reservoir to a low temperature, as per the Clausius statement, it is impossible for a cyclic device to transfer heat from a low temperature reservoir to a high temperature reservoir without any other effect. That is, without leaving any other mark on the surrounding, it is impossible to transfer heat from a low temperature body to a high temperature body over a cycle. During a particular process, it definitely is possible, but when we talk about a cycle, it is not possible. Like shown in this particular case, you have two bodies at temperature T1, or maybe we take temperature TH just to be consistent with the previous slide, and temperature T2, say let us say temperature TC. So, some amount of heat transfer is taking place, and it is always said that if TH or rather TC is lesser than TH, then the direction of heat transfer will always be from 1 to 2. 2 to 1 heat transfer is not possible unless we add some additional effects in the form of a heat pump or refrigerator. So, the second law of thermodynamics gives you the direction of heat transfer. The first law of thermodynamics defines, the zeroth law of thermodynamics defines the concept of temperature. Second law of thermodynamics is saying that there will be heat interaction between system and surrounding as long as they are at a different temperature, but it does not say anything about the direction of temperature, which is given by the second law of thermodynamics, which says that the heat transfer will always be from the high temperature to the low temperature, just like shown in this particular case. We do not need to talk about the concept of entropy here, but something else that we can add here, that in the form of the corollaries of the second law. There are several corollaries possible from the second law, but we are interested in only two of them, which are more popularly known as the Carnot's principle. There are two Carnot principle. In both the cases we are concerned about one high temperature reservoir and another low temperature reservoir. So, here the high temperature reservoir is given a temperature Th, the low temperature one is given a temperature Tl. And for the moment just forget about this third heat engine. Here we are involved with only two heat engine, one is engine number 1 which is an irreversible engine, and other is engine number 2 which is a reversible heat. Both are working between the same temperature reservoirs. Then the Carnot principle says that the efficiency of the reversible one will always be higher than the irreversible one, or to put in more formal term, the efficiency of a reversible heat engine will always be greater than the efficiency of an irreversible heat engine while working between the same two temperature reservoirs, so same two thermal reservoirs. So, that is the first Carnot principle, but here we are concerned about the second Carnot principle. Let us remove this one from our system. We have now 2 and 3, both are reversible heat engines and both are working between the same two reservoirs. Then the second Carnot principle says that both of them will be having the same efficiency. That is, in more formal term, the efficiency of any Carnot engine working between two given thermal reservoirs, any reversible heat engine or Carnot engine working between two given thermal reservoirs will always be the same. Now, what does that suggest? Here we are saying that once we are given with these two temperatures Th and Tl, the temperatures of the two reservoirs, then whatever may be the nature of your heat engine, corresponding efficiency of any reversible heat engine will always be some constant value. You can't change by changing the nature of the reversible cycle, it will always be the same as long as the temperatures Th and Tc are given. What does that suggest? Then this efficiency has to be a function of only these two temperatures and nothing else. So, this efficiency is definitely a function of Th and Tl, or as per our the notation of our efficiency, we know it can be written as 1 minus QL upon QH, where QL is the amount of heat rejected to the reservoir temperature TL and QH is the amount of heat added, that is this is QH and this is QL. So, this has to be a function of TH and TL, that means QL upon QH has to be some function of this two temperatures TH and TL. So, that is something that we have to make use of to define something called the thermodynamic temperature scale, or that single point temperature scale which we roughly mentioned in the previous slides. To derive the expression for this function f, like here we know that the efficiency or corresponding ratio of heat introduction is a function of only the two temperatures. Now, we have to identify the nature of this function f. So, here we consider this particular situation. Here we have three reservoirs, one at temperature T1, at T2 and T3. Here this T1 is greater than T2, greater than T3. So, there are three engines also, A, B and C. A is working between T1 and T2, taking Q1 amount of heat, rejecting Q2 amount of heat to T2 and producing WA amount of work. Now, B is working between T2 and T3, taking the same Q2 amount of heat which was rejected by engine A and finally giving Q3 amount of heat to reservoir at T3 and giving WB amount of work. And look at C, it is working directly between T1 and T3, taking Q1 amount of heat and rejecting Q3 amount of heat to produce work WC. Now, how we can say that this both of them will be equal to Q3? Because these two engines together can be replaced by a common engine in that which is working between the reservoirs T1 and T3, or in other way we can visualize engine A and B to be working together with each other or coupled with each other. In that case, this combined cycle or combined engine definitely will be taking the, when it is taking Q1 amount of heat, then definitely will be rejecting Q3 amount of heat, because all reversible engines will be having the same efficiency, and here A, B and C all three are assumed to be reversible engines. So, both are rejecting, both B and C are rejecting Q3 amount of heat to the reservoir temperature T3. Now, as per the derivation that we have done in the previous slide, we know that for the engine number A, we have Q2 upon Q3 or sorry Q2 upon Q1, that is heat rejection by heat addition, has to be a function of the corresponding temperatures T2 and T1, the temperatures between which this engine is working. For engine B similarly, heat rejected is Q3, heat added is Q2, that has to be a function of T3 and T2, and for the engine C, which is working between T1 and T3, then heat rejection, which is Q3, by heat addition Q1, has to be a function of what? Has to be a function of T3 and T1, is not it? So, if we combine them, Q3 upon Q1 is equal to Q3 upon Q2 into Q2 upon Q1, that is functions of T3 T1 is equal to functions of Q3 upon Q2 is a function of T3 T2 into function of T2 T1. Now, look at this expression quite carefully. This expression says that the left hand side is a function of only T1 and T3. However, the right hand side we have a product of two functions, one is a product of T3 and T2, other is a function of T2 and T1, but the left hand side is not a function of T2. Then when that is possible? That is possible only if this function f is a form something like g of T3 by g of T1 is equal to g of T3 by g of T2 into g of T2 by g of T1. Only if the f is a function of a functional form like this, that is the numerator is a sole function of T3 and the denominator is a sole function of T1, or in more formal term the numerator is a sole function of the lower temperature and denominator is a sole function of the upper temperature or higher temperature, then only this is possible. So, we know that now if T3 T1 is equal to g of T3 by g of T1. Now, next question is what is the form of g? Now, there are several functions which can satisfy this and our choice of function is completely arbitrary. So, we shall be going by what was suggested by Lord Kelvin. He suggested a very simple form where he suggested to take this ratio as just T3 upon T1, which is the simplest possible definition, and that is found to be work perfectly for all applications of this principle and therefore is always taken. So, what we are getting then? We are having now the efficiency for a heat engine which is taking QH amount of heat from a reservoir at temperature TH and rejecting QL amount of heat to a reservoir temperature TL. From them, efficiency of this reversible heat engine is given as 1 minus QL upon QH, and therefore, it is 1 minus TL upon TH, which is known as the Carnot efficiency. But for our purpose of this temperature measurement, we are not interested about this, we are more interested about this particular situation. QL upon QH is equal to TL upon TH. It is not at all saying that the QL is equal to TL, rather it is saying that the ratio of these two heat interactions will be equal to the ratio of the corresponding reservoir temperatures, and that provides something known as the thermodynamic temperature scale. Look at this, here we are saying that the temperatures of the two reservoirs are the ratio of the temperature of the two reservoirs is just equal to the ratio of the corresponding heat transfer. Now, think about the Celsius and Fahrenheit scales. There we specified those 0 or 32 values based upon one physical phenomenon, which is the melting of ice under atmospheric condition. Now, if the pressure changes, corresponding melting temperature will also change, and then we can't identify that new melting temperature as 0 because the condition has changed. That means the definition or of the references in those scales are dependent upon the properties of some fluid, which is not the case here. Here it does not matter whether there is some kind of phase change phenomenon going on inside T1 or inside T3 or something else. We are just directly getting that the ratio of these two heat interactions is equal to the ratio of the corresponding temperatures, and that is why it is called the thermodynamic temperature scale. It is independent of the behavior of any material and is an absolute relation. However, we still need one final parameter to define the scales, because it is only giving us a ratio of TL and TH. That is why we generally take the triple point of water in Kelvin scale. The triple point of water is given a value of 273.16 Kelvin, and of course, the absolute 0 is given a value of 0 Kelvin, and then accordingly we can put 273.16 number of subdivisions between these two temperatures to get the Kelvin scale working. Or you can say this absolute 0 actually a proper point which is independent of any fluid properties, and therefore, that should not be mixed with the ice point or steam point. But this is also a perfect parameter which does not depend, which is definitely the triple point of water, but it is again independent of temperatures and pressures. So, again absolute constant for this. So, the temperature scales which are defined based upon this particular principle, they are called thermodynamic temperature scales, or sometimes called the single point temperature scale, because we just need one reference point like this particular one here for Kelvin or Rankine scales. So, with this knowledge, let us move on to check out what are the different ways we can measure temperature. The first method, the more popular one or very popular one for domestic applications, that is the change in physical dimensions, something like the bimetallic plates or liquid in glass thermometer. Then change in gas or vapor pressure, constant volume gas thermometer and pressure thermometer, which can be gas filled, liquid filled or vapor filled. Then we can talk about the changes in electrical properties. There are several very popular options like the resistance temperatures or resistance temperature detector, RTD in short, thermistors, thermocouples, probably the most common use or common method for technical use, semiconductor junction based sensors. Then change in emitted thermal radiation, thermal and photon sensor, total radiation pyrometer, optical and two color pyrometer, and infrared sensors or infrared pyrometers. Changes in chemical phase, it is a much newer use and not that much in industrial scale, but more at research scale, like fusible indicators, liquid crystals, temperature sensitive paints, etc., all can be considered. Out of all these 5 kinds of categories, the first one, that is changes in physical dimensions, these are low cost, low accuracy applications. So, for domestic or for crude laboratory applications, we can always go for this. However, a more popular one is the change in electrical properties like RTD, thermocouples, etc., very popular in industries and also in scientific research. Particularly when you are looking for automatic control or remote sensing, then we have to go by something like this or more advanced option. And the changes in emitted thermal radiation, that is a non-conductive applications for very high or very low temperature sensing, we generally make use of them. So, today let us check out the first and second kinds. In the next lecture, we shall be talking about this third kind. Shall be talking about this third kind in second lecture, and in the third lecture we shall be talking more about this particular one. But today our focus is on this type A and B, which are more smaller discussions, and probably you already know about most of them. So, the first device that comes into mind is the bimetallic plate, which falls under this first category, that is changes in physical dimension. Here the idea is very simple. You have two plates, two metallic plates having different coefficient of expansion, and we couple them just like the one shown here. They are fixed with along the longer surface, but one of the end is also fixed. One of the end of this combined bar is also fixed, and the other end is free. Now, when the temperature changes, their coefficient of expansions are different, accordingly their modified lengths also will be different, but as they are strictly or they are joined together strictly, then it will be not possible for them to expand separately. So, only way out is to get bent. Just shown here under room temperature with the examples of copper and iron, they are joined together, they are having exactly same dimensions. Now, if they are not at all connected with each other, then copper is expected to have a larger thermal expansion with elevated temperature, like this much higher increase in the copper length is expected. but when they are bonded with each other, then of course copper can't bend or can't increase length without affecting the length of the iron part, and therefore what it does is it form a bend like this. Just look at this one here, definitely the red one is having, as it is on the outer side, it is having a longer length compared to the blue one which is on the inner side. And we can also have a clamp type of situation to measure the amount of deflection that has taken place, like it is fixed at one end and the other end is free, so it is bending, and we are measuring the amount of deflection that has taken place, and that can directly be related to the modified temperature, because under standard temperature or calibration temperature it was just perfectly horizontal like this. So, this angle is a measure of the deflection and subsequently the measure of the temperature. Quite often the radius of curvature of after the bend, I mean I am talking about this particular curvature, that is given by a relation like this. Here this T refers to, or let us say Ta is the thickness of bar A, Tb is the thickness of bar B, T is the total thickness, that is Ta plus Tb, and m is the ratio of the two, that is Tb upon Ta, and n is the ratio of the corresponding Young's modulus Eb upon Ea, and T2 minus T1 is the temperature range over for which we are doing this particular calculation, and alpha A and alpha B are the corresponding thermal expansion coefficients of material A and B respectively. Now, there are several situations when the thickness of Ta and Tb are generally taken to be same. So, in that case m becomes equal to 1, and it is also common design feature to have n plus 1 by n is equal to 2. When that happens, then this relation for rho takes a much simpler form. Then we have rho equal to 2T upon 3 into alpha minus alpha b into T2 minus T1. So, this T generally is known because that is a design parameter, alpha and alpha b are material properties, so they are also known beforehand. So, we can measure the change in temperature T2 and T1, or I should say T2 minus T1. So, that is how bimetallic plates works. That is a simple configuration, but there can be several possible designs of bimetallic plate. Like we can have a spiral type of design where the center of the spiral is fixed and the free end can expand and can accordingly move over this particular scale. Another possible design can be a helix, where you have a bimetallic helix, again because of the expansion, because of the thermal expansion the pointer can move over this particular scale. There are several advantages of such bimetallic thing, like we can have very low cost, simple and portable, we can always take them anywhere for measurement purpose, they generally are quite robust, and no power source required, which is a big advantage. And physical inspection is quite easy because you are talking about a small device with simple machinery. But the problem is they are not the most accurate one. They are not suitable for remote sensing also. You need to take the scale or thermometer in contact with the surface where you want the temperature measurement. It can't give you measurement from some distance. Time lag is there because the pointer needs some time to settle down at a particular location, like the expansion or the bending phenomena itself may take some time. So, it is suitable more for static measurement. Limited temperature range, because temperature range is limited by the properties of these two metals. Finally, insensitive at low temperatures and not suitable for digitization. So, while they can still be used for temperature measurement, but they are more popularly used for several other normal applications as switches, something known as the thermostat. In case of a thermostat, we have a bimetallic strip and we have this particular contact. Initially it is in contact with the metal strip, but if as the temperature keeps on increasing, the strip will get bent in this direction, accordingly disconnecting the contact beyond a certain point and thereby stopping the flow of current through this. The application of such kind of bimetallic strip you can find in domestic refrigerators when they keep on following some kind of on off schedule, and also sometimes in old grandfather clocks where as the temperature fluctuates with the time of day or with the season, they can provide accurate measurement of the time without changing the effective length of the arms. The other option, very popular one or the most popular one that you know, is the conventional thermometer. Something probably before this lecture you knew as the term thermometer, by the term thermometer, but this more specific name of this one is a liquid in glass thermometer, where we have a capillary filled cavity, or I should say we have a capillary tube through which we have some kind of liquid, temperature sensing liquid that can move up and down of the capillary tube. The picture that I am showing, that is having a horizontal orientation, but practical cases generally it is put in a vertical orientation, where we can see several components. Some of them are compulsory, but some of them are also optional. The first one is a bulb. This is a bulb which act as the storage of the fluid that we are using. So, we generally have a very thin glass wall which should be thin enough so that the fluid inside can sense the temperature of the surface in contact of which you are bringing this one, but at the same time it should also be hard enough to sustain minor vibrations or minor shocks. The volume of the bulb needs to be carefully designed so that it can house just enough amount of fluid to to provide reading over the entire volume of the, or provide the entire scale of this without overflowing the scale or without leading to any kind of overflow. And the thermal expansion coefficient of the bulb and the corresponding glass tube should also be compatible with that of the liquid. Then we have the, after bulb we have the stem. The stem generally made of annealed glass, depends on, and the property of the glass depends very much on the temperature range for which you are using, like the scale that you are using for measurement of sub-zero temperature may not be suitable when you are measuring temperature in the range of 200 or 300 degrees Celsius. And also it is important to minimize the effect of thermal expansion, because you have to understand that as the temperature of the fluid changes and its volume expands, similarly the volume of the glass also is expanding, and we somehow have to go for some kind of compromise, or the coefficient of expansion for the glass needs to be arranged such that its effect is minimal on the final reading, and that is why it is important to choose the material for the stem depending upon the temperature range of operation. And also the portion, the void portion, like here the dark portion refers to the liquid whichever you are operating with, and the empty void portion of the stem which is not containing any liquid at this particular moment, they should be pressurized by certain kind of medium, so that it can avoid the column separation of the mercury column and also avoid the vaporization of the fluid inside when the temperature increases. Then we can have an auxiliary scale. This auxiliary scale actually is an optional item, and this auxiliary scale refers to a scale which is well below the main scale. This is the main scale. This particular one is the main scale, which is the zone of interest or temperature range of interest. The auxiliary scale is generally refers to a temperature well below the main scale temperature, quite often used for calibration purpose, like it may refer to the 0 degree Celsius in case of a Celsius scale, which we may not be using under normal operation purpose, but occasionally just to check whether the thermometer is working correctly or not, we may would like to check this one with this auxiliary scale. The meniscus refers to the separation part of or the liquid filled part and the void part of this. Then we have this contraction chamber. This contraction chamber is again an optional item, optional in a sense that it is providing a slightly expanded volume within the capillary tube, so that we can manage the total volume of liquid that is going into the main capillary or towards the main scale, thereby somehow controlling the total height of the liquid column. This immersion line, certain thermometers may also have the immersion line, which is this one. This refers to the height up to which the thermometer must be immersed to get a proper measurement. So, if we are using this particular thermometer, then starting from this bulb up to this line, we want it to be immersed into the zone of application, and the rest part will be open to the atmosphere. And finally, we have this expansion chamber, which is a compulsory part, which is present in any thermometer. If there is a certain rise in the volume of fluid, suppose we have used it for a temperature which is higher than this maximum range, then thermometer will be expanding beyond the main scale, and to arrest that expansion we provide this expansion chamber. So, there are several possible liquids that can be used, but most popular one definitely you know is the mercury thermometer, which can operate over a range of -38 to about 350 degrees Celsius, because mercury starts to freeze around -38 degrees Celsius and its boiling temperature is around 350 degrees Celsius. So, while the boiling temperature is more or less okay, but the freezing temperature is quite high compared to several applications. We can lower this freezing temperature a bit if we use a mercury thallium mixture, then it goes to -56 degrees Celsius, which can be sufficient for if we are looking for say weather temperature measurement in the harshest of condition or in the toughest of conditions, but if we are looking for certain kind of cryogenic applications etc., this is still quite high. Now, mercury thermometer is everywhere, or I should say the liquid in glass thermometer and mercury thermometer are synonymous because of such widespread application it has. But the problem with mercury has several advantages of course, but the problem with mercury is it is toxic, and that is why several international organizations have nowadays recommended not to use mercury thermometer. Actually, ASTM has given a recommendation or a restriction that it is not going to calibrate any mercury thermometer from now onwards. So, it may happen that mercury thermometer may become a stuff for the museum in future, but may not be a very near future just because of its wide availability and applicability and ease of use. Now, the option for replacing mercury thallium composition or combination also has the same disadvantages. Now, the option for replacing them can be a spirit thermometer. There can be several organic fluids, or there can be toluene, alcohol, butane, they can also be options. One problem with them that they are opaque in nature, so it may be difficult to observe their rise, that is why they are often colored with certain kind of dye, red or blue color dye are very commonly used. Spirit thermometer has several disadvantages. Before we talk about its advantages, we should mention the disadvantages, like it is definitely less accurate compared to mercury, prone to vaporization because they have lower boiling temperature. They can have their surface tension is low, and that is why we may have discontinuous liquid column, thereby giving a wrong reading. They can form film on the capillary while coming down, and also their sensitivity, they have a greater sensitivity to changes in step temperatures, or I should say this should not be step temperature, it should be stem temperature. So, they have a greater sensitivity to changes in stem temperature. Because the coefficient of expansion of most of the spirits like alcohol and most of the common glasses that is used, there is not that big difference, and that is why they are quite sensitive to the changes in the stem temperature, but they have certain advantages. Okay. Another advantage is the disadvantage I should say, the dimensions of the thermometer will be different compared to the dimensions of the mercury. So, we properly need to do the calibration and also the calculation of the dimensions. But the biggest advantage for them is non-toxic, that is why they score over the mercury thermometer. Their lower temperature can be much lower, can go up to -200 degrees Celsius, thereby making them eligible for several cryogenic applications. That is again another point they score over mercury, and they have been suggested by ASTM because ASTM is not recommending or calibrating mercury or mercury based materials for thermometer applications. Another advantage that can be mentioned in this, or I should say another advantage of this mercury thermometer, that their cost can be slightly lower compared to the spirit based thermometer, cost can be slightly lower compared to the mercury thermometer. Another possible alternative can be something conventionally known as the low hazard precision thermometers or low hazard precision LIG thermometer. LIG just refers to liquid in glass. Low hazard precision LIG thermometers, which can be a replacement of mercury based thermometers. They generally use some non-toxic biodegradable materials, but those materials are proprietary items of the manufacturers, not clearly specifying the properties of this, but they may have be a future option. Now, another point that we have to be careful while using this liquid in glass thermometer is the level of immersion. How much should we immerse this? There are three kinds of situations. We can have total immersion thermometer, where the bulb and the entire liquid column that should be immersed. So, the only the meniscus, it should be just slightly above the container or zone where we are measuring the temperature, but entire of the bulb and the liquid column should be exposed to the temperature which we want to measure. This is probably the most common, or I should say the most advantageous kind of thermometer, most accurate option that we can have, but one problem is that how can we know how much should we immerse? That will only come from the after getting the temperature measurement and maybe going through a few trial and error. They are commonly used in constant temperature baths, where you want to maintain a constant temperature in some kind of liquid pool or container. This can be a good option. Then partial immersion thermometer, where we have a line specified, just like shown in the previous slide, immersion line. This in every situation it needs to be immersed up to this height at least. There are several scenarios where the length of the thermometer may be more compared to the depth of the container where we are looking for temperature measurement. So, it is not possible to go for total immersion, rather we go for the partial immersion, but we have to ensure that the thermometer is immersed up to this immersion line. And finally, we have the total immersion thermometer. In case of total immersion, the entire body of the thermometer is immersed. It is not a very common application. Thermometric fluids should have the following properties for making them eligible in LIG thermometers, like linear temperature dimension relationship, so that we can have a perfectly linear scale. Like if we you probably know that the temperature expansion for any fluid delta L, or if instead of writing delta L, if I write suppose delta V, the change in volume of any fluid generally can be given as beta V naught delta T, where delta T refers to the corresponding change in temperature, V naught is the initial volume corresponding to some reference temperature, and beta is the thermal expansion coefficient. Now, this thermal expansion coefficient may not be a constant. If it is a constant, perfect constant, you are going to get a perfectly linear scale, but itself can vary with temperature, and similarly the glass cover also can vary with temperature. So, the thermometer scale should properly take care of this. Large coefficient of expansion, this is where the spirit thermometers are better, because their coefficient of expansions are much larger compared to mercury, and therefore they can give much larger sensitivity. Reasonably wide temperature range as liquid, this is none of the options, that is mercury or spirits, are good in this sense, because mercury has a reasonably high upper limit of around 350 degrees Celsius, but their lower limit is quite high, whereas the alcohol based thermometers can go up to minus 200 degrees Celsius, but they starts vaporizing beyond 150 to 200 degrees Celsius, and therefore they are not usable at higher temperatures. Clear visibility within the capillary, mercury scores over spirit, because mercury is opaque and clearly visible within the capillary. However, alcohol is transparent and can be used only after it is colored with certain kind of dye. And the liquid should not adhere to the capillary wall, which is again mercury better, is mercury is mercury is better compared to spirits. So, you can see that there are several points, at least in terms of this one and this one, mercury is definitely better. This one, mercury is better for higher temperature side, alcohol is better in terms of this particular one, and that is why mercury thermometer is more popular compared to the alcohol thermometers, but because of this toxic nature you may see them completely out of market in next 30-40 years. These are thermal expansion based device. We shall quickly be talking about two more devices, or another category where we are using the changes in gas and vapor pressures, and the one that comes here is a constant volume gas thermometer. This is something that uses the expansion of gas with temperature. Here we have a fixed mass of gas maintained in a particular container. Now, this once we immerse this container into the environment, or expose this onto the environment where you want to measure the temperature, we keep the volume constant. As the volume remains constant, then its pressure has to increase, because from if this gas follows the ideal gas equation of state, we know that we have P1 upon T1 is equal to P2 upon T2 during a constant volume process. So, temperature will keep on increasing linearly with the pressure, or conversely I should say, as the temperature increases, pressure will keep on increasing linearly with this temperature. We generally have a mercury based manometer to provide us a reading of this increased pressure. This side is open to the atmosphere and this side is subjected to the pressure inside this container. So, the difference in this mercury column is going to give you the value of the pressure inside, and instead of pressure you can mark this particular scale in terms of directly in terms of temperature. These constant volume gas thermometers are actually the ones that gave us the idea of the absolute zero, because if we do experiments with different gases, you can find for all the gases the line extrapolated in the negative temperature direction converges to a particular point where the volume becomes 0, theoretically at least. Practically all the gases condense well below this temperature. However, theoretically this is the temperature at which the volume of all gases will become 0, and that is the one we marked as the absolute temperature. Now, constant volume gas thermometer generally is used as a reference for calibration purpose, but may not be for industrial use, because it is generally fragile. Again, you need to keep this one in contact with the body where we want to get the measurement. It is quite difficult to use for practical purposes, and that is why it is restricted only for laboratory purposes. By the way, I have not mentioned separate advantage or disadvantage for the liquid in glass thermometer, because those are quite similar to the bimetallic strips. So, you can just think about the same points, that is they need to be brought in contact with their advantage can be they are small, cheap, portable and quite well used, but disadvantage can be they can be fragile, and they need to be taken in contact with the body, so not possible for remote measurement. Now, constant volume gas thermometer has an improvement in the form of pressure thermometer, where instead of a fixed container or a rigid container, we are having a chamber within which we can have certain fluid, and as the temperature changes, its pressure again change, pressure, and that is sensed by this particular pressure measurement gauge. Here the container is connected with a long tube. The length of this tube can be very long, even in the range of 100 meters, thereby providing an option of remote measurement. That is, this particular part can be kept at one location, and the pressure measuring or the temperature sensor can be kept at a distance far away from this, facilitating the remote measurement. We can have a liquid filled option, where the medium is maintained specifically at liquid phase throughout. Now, liquids are more incompressible in nature, so as the temperature changes, the sensing will come more in terms of the change in volume of liquid. We can have gas field, where it is maintained completely under gaseous situation, and we can also have a vapor field, where we maintain a liquid vapor mixture, thereby as the temperature changes, corresponding saturation pressure also changes, and that is sensed to get the measure of the temperature. They have generally a very large operating range, much larger compared to the earlier ones that we have discussed. But for the gas filled ones particularly, we can have very wide range, limited only by the condensation of gases at the lower side and possible dissociation of the gases at very high temperatures. And there is no elevation effects as well, that is, they are independent of the effect of gravity generally, but the disadvantage can be large bulb size requirement, and generally they lead to very small deflection unless there is significant change in temperature. So, these gas or vapor pressure based thermometers are generally used more as standards or calibration purposes. In the next class, we shall be discussing about the electrical property based temperature measurements, which are generally more used for technical purposes. So, if we want to summarize what we have done today, we discussed about the laws of thermodynamics, defined the temperature from the context of the zeroth law, and the thermodynamic temperature scale from the context of the second law. We have discussed about the 2-point and single point temperature scales, then different methods of temperature measurements were summarized. Then we talked about the expansion based devices, two devices basically, one is the bimetallic strip and other is the liquid in glass thermometer. Then we have talked about the gas vapor pressure based thermometer. So, we mentioned about the constant volume gas thermometer and the pressure thermometer. So, that is it for the day. Next class we shall be back with the measuring tools like RTD and thermocouples. So, till then, thanks a lot.